Group 3-4's Lab 2 presentation. This lab investigates what happens when an instantaneous voltage is applied to an RC and RLC circuit by diving into a system's step response, system steady state, and other parameters like the time constant. Basic terms, an RC circuit is a circuit that has a resistor, capacitor, and some sort of voltage, and an RLC circuit has a resistor, capacitor, inductor, and some sort of voltage as well. Kirchhoff's loop rule applies to both circuits except that the RLC circuit has a voltage drop across the inductor while the RLC circuit does not. This loop law is the base for the rest of the equations using that the sum of electrical potential differences around a loop is zero. The importance of this lab is to understand how theoretical values are not always exact when doing real-world analysis due to error, and how this must be taken into account when designing a system.
In this lab, we tested the step response of RC and RLC circuits. We used decade boxes for the resistor, capacitor, and inductor. They all have error associated with them, so once we had them set to the values given to us, we double-checked them with an LCR meter. We then hooked the decade boxes together in series and then to the computer. We then used Lab2 to send a voltage through the circuits and record the response. We did this once for the RC circuit and twice for the RLC circuit, once underdamped and once critically damped.
For the RC circuit, the plot of the theoretical data was closely overlapping the plot of the experimental values for the voltage source. This tells us that the experimental data concurs with the theoretical model derived from the relevant differential equations. To justify this claim further, the experimental time constant of the RC circuit was determined from the voltage time graph and again from the derived error fraction time graph of the RC circuit. In addition to this, the theoretical definition of the time constant also yielded a value that was relatively close to the experimental values. Looking at the RLC circuit graph for the undamped response, we notice that the experimental values also closely overlap the values for the theoretical model. Using the same characteristics of the RLC circuit to create a critically damped system also yielded results that were overlapping. Speaking of characteristics, it is important to note that the experimental determined damping ratio was relatively close to that of the theoretical data. However, the experimentally determined natural frequency was relatively different from that of the theoretical model. This difference arises from the variability of the calculations for the damped natural frequency of the system, meaning if 3 overshoots were used, the result would be different from using 6 overshoots. A method to solve this could be to average the results from 3 to the most number of overshoots available.